The other things that I more clearly remember, of course, about what we talked about in those days was the subject which was really my all-encompassing subject, that I wanted to know what could be done about building computers with electronic vacuum tubes as the main elements and to get some speed and so on. And as I talked to Eckert about this, which I certainly did then, why, I was considerably cheered up, because he thought this was a very sensible idea, that why not, you might say, do things like this. It didn't seem to him beyond possibility at all. He didn't say that he knew the answer, but it was just that in the kinds of work that he had been doing, why, he had to attend to all kinds of design problems, including reliability. He had, for instance, designed a smoke measuring device for somebody's smokestack. So he had to make that so that under the conditions of being wherever it had to be to measure the smoke in the smokestack, that it gave reliable readings. And so for him, he undertook this just as an engineer should undertake it. This was a question as to what are you trying to accomplish and what have you got to do it with, and let's take account of the peculiarities of the things that we're going to use, such as vacuum tubes and such as other components in an electronic circuit, maybe the batteries or whatever powers them. All of these things the engineer has to consider. What are they likely to do so that they will perform as they're supposed to perform and to be a reliable product. As of today, for instance, why some people are wondering about the Con Edison system in New York City, which just had another blackout. How do you test it? Well, fortunately, the kinds of things I was talking about with possible computers built out of vacuum tubes, there are all kinds of ways of testing, and it wouldn't lead to any problems as to anybody doing without light or without subways or without elevators or anything else. None of the difficulties that you might have in testing a real system on which a whole city depended. Here all we had to do was to build some things and test them and see whether we designed it. So if you have the right design philosophy, I was convinced by Eckert that he had the right approach to this, the right attitude toward design, that when he said, I don't see why we can't do it, that he really was seriously saying one ought to try it. Okay, but we had to have somebody, of course, to say, here are some funds to try it with, and what are you going to use it for, and nobody's going to give you funds in a place where we were, which were just for exploring a new device out of which you might make a profit. That's what an industrial place might try to do. But the situation we were in was that there was a world war coming along, it seemed. It was already in Europe. We might be drawn in, and there were already evidences, I think, that there were various ways in which the Moore School was going to be involved. Sometime I learned, for instance, that the differential analyzer, which was a big computing device which was right there in the Moore School, and which had been built during the Depression with government funds, was promised as a computing tool for Aberdeen Proving Ground should they ever need it. That it was a resource which the Aberdeen could draw on should they require it. And so, even though at first I saw General Electric Company coming down and using this thing with Corny Wygant and other people helping them as they did so, there came a time when the Aberdeen Proving Ground took over the operation of that analyzer under their previous arrangement and started computing tables which were called firing tables to tell an artillery officer which way, how to adjust a gun so that it would hit the target. And with that kind of application in mind, why we began more and more to think in terms of perhaps the close relationship between Army Ordnance and Moore School would result in their being able to support the development of an electronic computer. Who else at that point? If it's going to be a wartime project, why, you've got to find a wartime need, you might say. In peacetime, I guess I might have tried at that point to sell the Weather Bureau, because that was the big application that I had in mind when I started out. But in this case, the Weather Bureau was as distant as anything. I knew they needed better weather predictions for war, but here was somebody who couldn't even shoot the guns until they had a firing table. And that certainly is a wartime project of very high priority. It turned out that the people that came to Philadelphia from Aberdeen to see how things were getting along were more and more disappointed by how slow the computations went. They decided they couldn't get enough done on the analyzer, and they started hiring girls. My wife was one of the girls they hired first, a math major. They hired some other math majors. Turned out very soon they exhausted the supply of available math majors, and they had to turn to hiring girls who had some ability and who could be trained to do calculations. So some of them were trained to use desk calculators, these mechanical things that were driven by an electric motor, but they were essentially mechanical in their operation. And so a dozen of them, then 2 dozen, then 3 dozen, more and more of these machines kept appearing at the Moore School and in surrounding buildings on the campus there for teams of girls to do calculations of this sort, to produce more and more firing tables. And it became the watchword around that although there were guns being delivered by American industry to the shores of France and so on, that they were useless because they didn't have firing tables to go with them. And so this more and more appeared as a high priority project, and I made it my business to see what was involved in the calculation of the firing tables. I went and talked to some of the girls and their supervisors, most of whom were men, to find out what I could about how these tables were computed, what operations, steps they went through. And of course, Corny Wygant and others could tell me something about the differential analyzer. And with more and more effort on my part devoted to finding out about these things, why I learned something about how the differential analyzer could be used in computing these tables. It might take a girl a couple weeks copying numbers and punching numbers back into the machine and so forth, and working on a big sheet of squared paper before she completed what they call one trajectory. That's just one flight of a shell from the muzzle of the gun over to the target. A couple of weeks for that, say. Whereas down at the differential analyzer, if it was in proper adjustment so they could depend on its accuracy, you might get the same thing done in, say, 15 minutes to 30 minutes, or something of that sort. One might ask, as I think many people did, why can't you just turn the gears in that mechanical machine faster and get things to come out twice as fast? Turns out that a lot of things go wrong when you do that. It's like asking if your automobile can make the trip to Harrisburg or someplace in an hour, Why can't you get there in a half hour? Just by driving twice as fast. The tires wear out faster, all kinds of things, the pistons of the engine, everything wears out faster, and you may even lose the ability to control the automobile and have an accident when you're going faster. So, with that differential analyzer, if you tried to run it at twice the speed, you destroyed some of the accuracy, and it was already tuned, you might say, to get all the accuracy they thought they required. And a lot of things about it. It would wear out faster. There were what they called strings and bands, threads around some torque amplifiers on the machine, which had to be readjusted and tightened up and replaced and so on at various times. All of this maintenance had to be done. Driving it twice as fast didn't do the job. So, as far as I was concerned, why, I had no fear about driving electrons faster and faster in a vacuum tube, although there's a limit there too, of course. Just because you can count at 100,000 a second doesn't necessarily mean that you can count at 100 million per second. There are things in electronic circuits which refuse to go as fast as you might want to drive them. But the big point about the electronic method was that the electrons are small, they didn't wear out, and so we more or less could count on a certain speed of operation for a certain cost of vacuum tubes, and we estimated that for putting the same amount of money into a vacuum tube device, we might run anywhere from 100 to 1,000 times faster than any computer that anybody knew how to make then. Well, people were worried about whether the computer would wear out in the ways, for instance, the vacuum tubes burn out. They have failures which just end their useful life, and you have to find out which one's burned out, plug another one in, and start all over, and so on. So there were lots of people who were anything but enchanted with the idea of electronic computation because vacuum tubes burn out. And consequently, you might have thousands of tubes in this machine, and not only do you have the difficulty of finding which tube is burned out and replacing it, but if that happens often, why, how is this going to help you? Because every time that happens, the machine essentially stops. You may have to do a certain amount of work over again even to carry on. So there were all kinds of reasons why electronic methods looked very bad, very pessimistic people. How could you convince them? Well, the only way to really convince, of course, is to build one and try it. But we weren't at that stage of desperation in 1941. And in 1941 was when I transferred from the course that I was taking on defense training, as they called it, onto the faculty of the Moore School. And that meant I had to resign from Ursinus College and secure them a replacement who was a very nice University of Pennsylvania fellow who had an interest such as mine in making good demonstrations to the students, things of that sort. So I found that when I was talking about these advantages that I saw for a computer of electronic type, why, I had lots of objections as to, well, it wouldn't work this way, it wouldn't be, and just in general, negative thoughts about this, and you can't get anywhere that way. The people who were being so negative didn't help me a bit, because I thought that what I'd learned from Eckert's comments and what I knew about computation, which was considerable, that practically everything they said had an answer, but it wasn't necessarily an answer that the other people believed in. So how do you get this confidence, or how do you get over the hump? Well, what happened was the war got worse. That's what happened. In other words, for the first 2 years there, from 1941, when I transferred to the Moore School, to 1943, I did quite a little talking to people, including some people from Aberdeen. And the most significant comment I got, I guess, was that of a man from Aberdeen who said, well, it sounds interesting, but it would take you at least a year to build this machine. By that time, the war will be over. It turned out that 1 year later, in 1943, the war wasn't over, and they were feeling even worse the pinch of not being able to compute the firing tables as fast as they could deliver the guns. Part of the trouble, I understand, was that they were fighting on new ground, or so to speak, on new sand. They were sometime in there beginning to fight a war in Africa where the resilience of the ground made the recoil of the gun behave differently. The firing tables that had been developed up to that time were such that they didn't give the right results for the desert. Whatever the trouble was, why the Aberdeen Ordnance people at that point made a change in the assignment of people to Philadelphia, the Moore School, and they sent up a man named Lieutenant Goldstine, who had just recently come from courses in which he had learned something about artillery and ballistics and so on, under, I don't know, Dr. Bliss at the University of Chicago and such. At any rate, they assigned him to the Moore School, all the operations going on in Philadelphia, with respect to various calculations they needed. And they assigned him to do whatever is necessary to try to get things done faster. Expedite this now. Okay, how do you expedite? Well, one thing he fortunately did was to say, maybe there's something to this electronic idea. He listened to the idea that maybe vacuum tubes could do it better, faster. So while he was at the same time in charge of seeing that the analyzer room people put out things as efficiently and fast as possible, and seeing that other girls were computing other things as best they could, why, when he came across this idea of the electronic computation development, he decided that he better act on it. That was his mission, really, to expedite computations. He didn't quarrel over the idea that it might take a little while to build such a machine, because by that time nobody was making any predictions as to when the war would be over. I think maybe they weren't even predicting who would win. So it's all out now. And so they, his argument, as he said it to me at the time, was, that the ordnance people spend millions of dollars getting General Motors to build them a tank that shall test out, and then they will discard the tank and say, no, it isn't what we want after all. So there's another $1 million down the drain, you might say, because it wasn't quite what they expected, or didn't work the way they wanted. Why not spend equal or similar amounts of money on trying out an electronic computer? And, well, one of his first reactions was, why don't you write this up? What we need is a memorandum. I said, I've written one. Well, where is it? It was lost. I've soon found out by trying to get a copy from Dr. Brainerd and Dr. Chambers and Dr. Warren, and I don't know whether Corning-Wygant had one, but I'd tried to distribute these things to all the colleagues I had at the Moore School there. And in particular, I was counting on whoever had charge of getting contracts with Aberdeen to put this into the pipeline where Aberdeen would consider it. Well, nobody could find a copy of this memorandum. Fortunately, however, I had a girl, a Sinus College graduate, who had a lot of information a lot of study of Latin and Greek and shorthand. And she not only knew English grammar, she knew lots of other things which enabled her to reconstruct from her shorthand notes exactly what had been written before. And when she produced that, why, there we had what is now known as the August 1942 Memorandum. When that time came, why, everything was very hectic. So Eckert and I hadn't finished writing the proposal at the time that they'd set the meeting for. And so we were working all night to try to finish as much as we could of this proposal. And then that very next morning, you see, while we were still reeling from the work all night, why, Goldstine got his car, put Eckert and me in the back seat, and drove out to Paoli, where he picked up Brainerd, who had just had his breakfast. And I don't remember whether we had much breakfast, but point was to drive down to Aberdeen and get that report under consideration, because there was going to be a meeting. When we got down there, we'd spent all the time on the ride down in the back seat of the car trying to pencil out further notes as to how we were going to complete this report. And then when we arrived at the Ballistic Research Laboratory, why, Goldstine saw to it that we were put in a room with a secretary nearby so that we could try to finish as much as we could, and the secretary would type these things. And so we worked and we worked and we worked, and the meeting went on somewhere, we didn't know where. And after a while, we got hungry, but nevertheless, we still thought that we could do best by continuing to work on this report, get more typed pages ready. And we did that. And then sometime in the afternoon, why, we were invited to come in to an office or room where Colonel Simon was and meet with him for a short while until we left. We were told that it had been decided to go ahead. So I don't think we even met with most of the people who had been at that meeting. Then the next disappointment came, I might say, as far as the day's activities were concerned, in that it was time to go back to Philadelphia, and so there was a Pennsylvania Railroad train a couple miles away, you know, the way Aberdeen was arranged. And so Goldstine said he would drive us over there, but that he was going to stay in Aberdeen, and so he was not driving back to Philadelphia, and so we could get on the train and go home to Philly. Fine, except that we were still hungry. But unfortunately, everybody else had a wonderful lunch at the officers' club, and they kept discussing it on the way to the station. It wasn't exactly our dish of tea, you might say, because we hadn't had any lunch, and I don't remember any breakfast. And so there we were. But while we were waiting for the train, why, we almost got a sandwich at the restaurant, at the station. And then we got on the train and went back to Philadelphia with Brainerd. And it was some other day that we again saw Goldstine, who stayed in Aberdeen to do whatever his job required. But the main idea after that was that there's sufficient agreement had been reached so that even though there was not a formal contract, that it was understood the University of Pennsylvania would go ahead getting as quick a start as they could on this project, and that a letter of intent, which was a rather usual thing to do in such cases, a letter of intent would be given so that everybody would be assured that there really was going to be a contract, and it was just a matter of formality, you might say, for the people in the high offices to get together, Mr. McClellan, I guess, and others for the university, Brainerd and so on, and whoever down at the Pentagon had to negotiate and sign these things. That part of the paperwork and arrangements were not anything for us to do. Our job really was to figure out now where we were going to get some people to make this project really come to pass. Now, we got the people, and I don't know just how we did it, because I, as a outsider, as it were, coming to the Moore School from other places, didn't know the engineers that were necessary, whereas Press and some of the professors at the Moore School had pretty good ideas as to where they could find some of their former students.
How about, if he looks at me, now he's almost looking at the camera. How about those lights in your eyes? Is it bad, or is it?
Well, as far as
a little bad, but you don't want to look up, I guess.
I was going to say, I can stand the lights. It's, the heat eventually is cumulative, you might say.
You know, when we get started, when Jim tells us to, of course, you were at the point where you were talking about getting a staff, of course, or rounding up people.
That's right, yes.
But before you do that, I would like to know, are you almost ready to go, Jim? But
well, I could now.
I'd like you to tell me a little bit about the mood on the train when you were coming back. Were you?
I can't remember it.
You can't remember you were really excited or elated or anything? No. You just were sort of worn out.
We thought, yes, we were very. Yeah, I didn't
so you really
I didn't want to put in the part. I thought it would be inappropriate here to put in about how at the train station why Brainerd got another meal, but we didn't.
A second meal? You hadn't had your first?
I don't know whether it had breakfast, you see, but when we got to Paoli, why we had to wait for Brainerd to finish his oatmeal or something. His cereal was still too hot or something, you know. So we waited a little while for him to finish his breakfast. And darned if I remember whether we got any, because although quite often when you work late, you'd go down to Linton's. Linton's an all-night restaurant there. But we didn't even have time to do that, you know. We were getting this report and trying to be ready to go with Goldstine at the time that he came to pick us up. And that was our schedule, and we tried to maintain it. So, when are we live?
Are we going on? Are we? Okay, keep on then. So then you want to go back to about your staff and collecting or trying to round up people for the project?
Well, I thought perhaps I ought to explain what kind of a staff we had. Here I was, by that time in 1943, I'd spent 2 years at the Moore School. And during that time, I was carrying a regular teaching load for various measurement laboratories and other things. And I'd begun to work with Dr. Pender on teaching some of the senior classes, exciting topics which involved the use of matrices in power line calculations for three-phase networks and so on. Well, with all of that, we were also then in the thick of war work. Remember that the course which I had taken in the summer of '41 was to try to find people who would augment the technical competence in electronics which this country was deemed to need. And so here I was continuing at the Moore School to help replace the teachers, like Dr. Travis, who had been taken away to go on his Naval Reserve duty. He was a Naval Reserve officer and immediately had to leave at practically the same day that I arrived. He had to leave. This was a disappointment to me because I'd known that he had offered the course on computing machine theory, and which I'd tried to take, but there weren't sufficient people wanting to take that, so that the time that I knew about it and wanted to take it, why, it wouldn't be given. Now he was leaving entirely, so even though I was coming to the Moore School in '41, I didn't have any chance to profit by anything I might learn from him. Well, there were lots of others still at the Moore School, but they lost another man, Knox McElwain, who had been my first teacher of electronics down there. He went to manage some of the manufacturing facilities for the Hazeltine Company. And so with several people gone during the war, why, they needed extra staff members for teaching, because the number of students didn't decrease. Instead, in addition to the regular civilian students, we had Army student training people, and we had a Navy training course to give, and I'm not sure now just how many other training courses came to increase the workload from the teaching point of view. But at any rate, the work of teaching at the Moore School continued during the war, and so they needed to keep their staff going, and that's why Dr. Burks, as well as myself, were asked to stay on and help to do that. But at the same time, we were involved in what was called first defense work and later called war work, contracts with the government to try to aid various aspects of the military's competency and equipment. And one of the things that was done was to get a contract with the Navy to see whether we could devise a way where a big coil of wire carried by an airplane, the coil being almost as big as the plane, would be able to sweep magnetic mines out of a harbor. And so we made a lot of calculations as well as a lot of experiments on that. The Navy provided the plane, and Art Burks and I did a lot of the calculations as to what fields possible and what the effect might be. But subsequently, I worked on a Signal Corps project which Dr. Brainerd had secured, and there I felt all the more strongly the need for some kinds of faster computational devices. What did the Moore School have to help in this computation? Well, as I mentioned, we at the Moore School had a differential analyzer, but that was fully occupied, of course, with the firing table work and wasn't available for the Signal Corps computation, even if it had been something that could be used. No one would know how to do with this analyzer what Dr. Brainerd had agreed in a contract with the Signal Corps to do, namely to use Maxwell's equations to integrate all over the surface of various reflectors to see what the pattern would be for a radar unit, and to get the sharpest definition, you might say, of targets, and to get the least signals getting back from the rear side of the reflector. You wanted to make your big parabolic dish, as they referred to it, as effective as possible in picking up planes and other military objects at a distance. And it was our job to study the pattern which might be obtained by reshaping that parabola of revolution principally by cutting out sections of it or adding to sections of it, which was thought to be a possibility in improving the sharpness of the focus. Simultaneously with the time that we were making calculations on this, why some other people, and I think that included Art Burks and several others who were Moore School graduate students at the time, going up on the roof and experimentally measuring patterns with similar types of antenna, that is, pieces of parabolic shaped material, but with holes or little edges chopped out and so forth, to see what difference that would make on the pattern. So while they were doing this experimentally on the roof of the Moore School, and that roof was only 2 stories high at that time, we were supposed to calculate the same patterns that they would measure from theory. Well, that was a little easier said than done. First of all, no one really had an idea as to just how you would do that. Theoretically, it was possible, but Dr. Brainerd just handed me a textbook written by Stratton, I believe, at MIT, and said, well, everything you need to know is in here. And so I found indeed there was a vector equation which described the general way in which you could calculate a field at a distance from a radiator. But the details of how you could do what we wanted to do were not there. And we puzzled over this a while. I set up a system that overcame obstacle number 1, you might say, how to do it from the point of view of theory. Obstacle number 2, though, was what are we going to use for a computer? As I say, with all this background I had, trying to figure out how nice it would be to do all kinds of things with a fast electronic computer. There were no fast electronic computers. And unfortunately, I found out there weren't even any slow computers around the Moore School. The calculating instrument, the differential analyzer, which they had arranged to get during the Depression, that was a wonderful boon for many kinds of engineering work. But when it came to any extra calculating equipment, they had just one small desk computer, which had been acquired apparently just to try to run a few checks on the differential analyzer, and was never thought of as a real way of doing any important research computations. So we had to somehow work out not only a digital technique for doing this job, but we also had to work out the strategy of where can you find computers. Well, may be forgotten now, but as soon as the American forces got into the war, the people that made desk calculators, multiplying machines and so on, all put their factories to other uses. Fire control devices and fuse things for artillery shells and so on. All of this were important things from the war's point of view. And calculation was not considered important if we're just talking about desk calculators that somebody might do a payroll on, do some accounting jobs in the office. Why, they weren't important. So therefore, if you needed the calculator, why, you had to have a priority. Well, how do you get a priority? Well, it's sort of like waiting in line. It's a rationing process, really. And so I found out that some of those calculators, which I had been anxious to buy and were offered to me before the war, they were offered for a price which I didn't have the money to buy, of course, then. Now, even though we had the power of the government behind us to try to get more calculators, why, we were small potatoes, you might say, compared to other users such as Aberdeen itself, which obtained a lot of these desk calculators for a lot of girls to use to try to supplement the firing table calculations. So it might take a couple months, even if you had a priority, to obtain one of these desk calculators. And after all, I think Dr. Brainerd had promised that in those few months, we'd have this job done. I don't know that anybody had an estimate then as to just how many calculators or how many people it would take. But finally, we located two sources and got the job finished in a fair amount of time. The one source was known to me immediately was that I had squeezed out of the budget at Ursinus sufficient money to buy one Monroe calculator, and when I left there, it was the property of Ursinus College. I thought, well, I guess I can get that one. And when I tried to do that, I found that there were all kinds of reasons now that the college just had to have an had to have a Monroe desk calculator with an automatic multiplication feature. It never occurred to them that they had to have that while I was there. But once I'd sold them the idea that they ought to be able to allow a little budget for that, why, suddenly it developed that everybody needed this for averaging grades and all kinds of important work. Well, I wrote some correspondence to the presidential assistant out there, Mr. Halfrick, and finally obtained this the transfer of this machine. We bought it from Ursinus College to help in my work with the Signal Corps project. The second source was the Wharton School. There were lots of calculating machines at the Wharton School, at least so it seemed to us. I mean, there were probably a dozen different types of desk calculators in their statistical laboratory, as they called it. There was where the business students could run various calculations, like in business statistics. They might want to do a correlation and various kinds of calculations which the Wharton School expected their students to do in the course of their undergraduate work. And so we were able to borrow the whole mess of machines from the Wharton School during at least the period when they had no use for them, and that was, for instance, during the Easter holidays and things like that, that when their students were away, well, we could make use of these machines. So, where do you get the people that run them? Well, some of them may have been from other departments of the university, but we actually were employing some of the undergraduate electrical engineering students whom I taught to push buttons on these machines and write down numbers and put in numbers and so on. And so with a staff of that sort, a dozen or so students who were using calculation forms which we had worked out for this particular Signal Corps project, why, we went through and calculated these antenna patterns to compare with the ones measured in practice by the engineers on the roof. It turned out the check was pretty good. What we measured and what we calculated and what they measured were in fairly good agreement. But we could have calculated all this thing more accurately and faster, of course, if we'd had an electronic machine of the sort that I was hoping someday would be available for weather work or what. So that was the kind of project which I got into during the first 2 years of my work at the Moore School, in addition to the teaching.
Could you stop there for just a minute?
No, I didn't say he'd been given graduate school at Moore School. I was on their mailing list, and so each year I would get a flyer of 3 or 4 pages of the evening graduate school courses mailed to me at least once a year, probably twice a year for each semester. And it would name all these courses with a brief description of each one. And one of them was the course given by Dr. Travis on theory of computing machines. And so I went down to him once and talked to him about the possibility of taking this course. And he said, well, I'm not sure when it'll be offered, in the sense when it'll be given, rather, because we have to have enough people, you know. They charge so much per semester hour, and they have to pay the professor for his evening graduate school work, which was an extra emolument. And so if it didn't have enough students, well, they couldn't pay the professor. And so they had to wait till I had 7 or 8 students registering for a course before they'd say, this course is going to be given. And I was in that situation later when I was teaching the acoustics course. What
would that course have been? What would the description of that course?
Well, I never took the course. All I know is the description. I can't remember that exactly now, but it talked about integrators of planimeter type and things of that sort. There were various kinds of machines which are historically known, but including things like a planimeter, which is used to measure the area on a surface of a map, for instance, by tracing the contour, the boundaries of that area. Why, you then can read off from a little wheel which has been trying to pick up motion from the piece of paper which you're using this on. And according to how much that wheel is turned, why, you can tell what the area is that's enclosed by that boundary on that map. Of course, it's scaled, but that's easy enough once you know the scale factor. Why, you can multiply by that easily enough. These things are essentially analog devices. That is, they can't go with infinite precision. They merely give you an estimate, as nearly as you can estimate the reading of the wheel, and allowing for the little slippage that might occur when the wheel should have turned and didn't, and things of that sort. But there were various inventions of calculating devices like that in the past few centuries, and so that was part of what his course was about. Another part, I think, probably had to do with finding not only finding the roots, but rather for devising electrical engineering methods for finding the roots of polynomial equations. And they'd had some graduate students there who had built things which look very much like generators, where a lot of machines on one shaft, say, and each with a different number of poles. Why, one of them could be generating voltages which were characteristic of a vector in a complex plane rotating at one frequency, and another one would be twice that frequency, and so on. So you could find the complex roots of a polynomial by using this equipment. However, the equipment was pretty hard to build to begin with, pretty expensive, and had limitations. In addition to the fact, of course, that, again, as an analog device, why its accuracy was limited. This only gave you approximate results. Well, what I wanted to get to, what I was talking about, was how we spent those first 2 years before the ENIAC computer project came along. That in all of this, you must realize that as soon as we were in the war, the question of who is going to help you do anything was more and more crucial. The reason we could do some of that Signal Corps project was because we did have students available to put to work for the kind of work that they were doing. Was essentially just high-class clerical work, you might say, following the directions I gave them for what buttons to push and what numbers to write down. Things of that sort. What column you write this in, what column you get this number from, and so on. So it was really what you might call a cookbook kind of job to do those calculations. Once you figure out the method and lay out the scheme for doing them. And so all I can say there about my own experience was that having had lots of different computing jobs in the past, why this was not an unfamiliar thing for me to try to do, and made use of my background in computation, which went back in part, for instance, to work helping my father at the Department of Terrestrial Magnetism, and in part to the work I did later myself, because I had to do my own computing, of course, at that place for any statistical job I had. And during my graduate period, I'd worked at the Bureau of Standards in the wind tunnel and such places. I had to do various kinds of computations there. And I was familiar with a number of different ways of using conventional calculating equipment, plus having read books on how to use punch cards for computing. Even though I didn't have a punch card machine available, why at least the theory was plain, how you do it if you had one. So I had also, before I arrived at the Moore School, gone to the World's Fair in '39 and seen what was then available, and what more impressed, you might say, by what was not available. I neglected to mention before that the most interesting thing, perhaps in the way of punch card calculation, was shown then by Remington Rand. They had a device which didn't take up much floor space. It was only maybe 2 feet by 2 feet, which would read punch cards and compute the product of two 6-digit numbers read from those cards, and punch that product back on the card, and also print all this information on a wide strip of paper like a big adding machine. And it would print the two numbers that were the factors, and it would print the product. And it would do this at the astounding rate of something like once per second. In other words, 1 card a second. Now, the IBM people had to take many seconds to get a product computed off from a card in the same way, two 6-digit numbers multiplied together. Their system was quite a serial system, you might say, whereas the Remington Rand people had found a way of using partial products to keep the whole thing done in a more efficient and somewhat parallel fashion. Well, that kind of knowledge helped me later in the ENIAC, for instance, in trying to get the best speed out of that machine. Because it was our job to not only build a machine that worked, but to make it work fast enough so that it would be useful. But let me say something more about the acquisition of personnel. As I say, we were fortunate having some students to help us in the computations for the Signal Corps. We couldn't rely just on students for our later work on the ENIAC. what you needed then were engineers, but that's graduate engineers. But what was happening was there was a draft which would take all the young people they could for the military service. There was also a spirit of lots of students and young people wanting to enlist, get in that war. And so partly for that reason why help was scarce, and partly just because people were drafted whether they wanted to go or not. And so one of the machineries that we had to cope with all the time was, how can you get somebody deferred? How can you represent to their draft boards that they are more useful to the war effort in the job which you have for them than they would be manning the front line trenches or something of that sort? So that situation even occurred with respect to me, of course. There I was, something like 37 years old when I came there, and to the Moore School. Or was it that? Let's see, born in 1907, and well, if we're talking about 1941, why, it's...
6.
So, at any rate, so I had a draft board looking at me too, you see, out in Collegeville. We had to tell them what I was doing and why I was useful doing what I was doing. And my utility presumably was that I was training engineers who would then be useful in the war effort, and that there was a technical type of war now, you know, and you needed all these technical people. So, as I say, I did not know where all the engineers came from who were found to start on this new project in 1943. The ENIAC, the Electronic Numerical Integrator and Computer, just making up a name for it, which someone in the Ordnance Department did, was not the way to get the people. In fact, the project was classified. It wasn't secret, but it was considered confidential, and therefore you couldn't go out and tell everybody what you were doing. And so you had to get people without being able to describe to them exactly what you wanted or what they might be doing. But the people at the Moore School, as I say, had graduated engineers in the past, and they knew where some of them were working, and somehow they laid their hands on people like Bob Shaw, who was a Princeton graduate originally, but who had apparently studied electrical engineering at the Moore School. And he brought with him a young man named Gale, who he thought was a necessary assistant for his work. And then there was Kite Sharpless, who had been a secondary school teacher in a private school up in Massachusetts, who would come back, I guess, to the Moore School to get some additional degrees for helping his teaching. And he was available there and had worked with Eckert preceding the ENIAC job. They'd been working on another wartime project, which was for the radiation laboratory at MIT, on ways of dealing with the time that takes for a radar signal to go out and bounce back and be received, which of course is